All right, so hello everyone. My name is Yadong. I'm doing presentation today on behalf of Ziye Yang and Ziye. They cannot travel today, so I will try my best. But today we're going to talk about accelerating function as a service and container image construction using IPU. I want to set the right expectation today before we get into details. So you can think this is more just a new proposal, an idea. There are still a lot of work to do to drive this into next level details. But we think it's a very interesting idea which might open up a lot of innovation opportunities. A quick overview of today's agenda, right? First, I will spend a few minutes just to provide some background and explain the motivation behind this idea and the proposal. And then talk about how the IPU can be used to help accelerate some of the function as a service, right, workloads. We will also get into some detailed design to explain what exactly that means, like what kind of actions, operations it takes, and how to move that operations into IPU to help offload the host workloads. We also did some POC, and Ziye Yang basically shows some like examples, commands line level details to show how to do different options to explain the offload model. Then we have a quick summary, okay? So motivation and backgrounds. So first, I mean, everyone knows this, but just quick recap, right? FaaS stands for the function as a service. There's a definition from Wikipedia. Is basically a category of cloud computing service, which really provide the platform level capability, enable customer to develop, run, manage application, right? Without any complexity of building applications and the infrastructure. So, but more importantly, typically function as a service, this just means functions, right? It's short programs. One of the challenges for function as a service is to get rid of all unnecessary overhead, right? Because these are the functions, very elastic. So you want to run as quick as possible. You don't want to spend a lot of time just to prepare the containers, prepare the images. So anything help to get rid of that overhead will improve this function as a service application and workloads. So the main overhead comes from a few places. I mean, first, typically, because function as a service it's functions, so typically you just write code, right? So someone need to compile the code first into a executable binary, and then you have to pack that binary with all the libraries you need, right? Put them into a file system. And then get the container, because this function runs inside the containers, right? So get that container environment up running as fast as you could, so you can improve that elasticity and the scalability of function as a service. Right, so basically, the preparation of overhead keeps coming from a few places. First, I mean, basically, build that container image very quickly, and get the execution environment ready, right? Which means if you download a container image, now you need to unpack the image into a file system as quickly as possible, and also expose that file system and bundle to container, so the host can start to run that function as a service application in the right container, right? And then a different way to phrase, basically, there are a few steps which basically really introduce a lot of overhead. One is image pooling, and then get the file system bundle ready, right? That's one. And also start a runtime shim before the container can run. So IPU can be used to really help accelerate a few operations. For example, the container image pooling, file system bundle preparation, right? Because the IPU, some of you probably know very well, we have a vision that the IPU will be the control point in data center, deal with all the infrastructure service offloads, right? So this kind of operation, like get the right container image, do the image preparation, unpacking, are perfect to do in IPU. And once you move that operation into IPU, there are a lot of accelerators available because typically you need a decompressed image. So now IPU has, I mentioned earlier in my previous presentation, which can accelerate the basic decompression, right? Can really improve that performance. So that's the benefit to do this in IPU. And then IPU also has a local storage and the local memory. So if you have a lot of containers share the same image, same root file system, right? You can catch that in the IPU, so which can improve efficiency as well. So I will do a quick intro of IPU, but I actually wanted to skip this section because I explained the Manavins in previous presentation. And we use the NVM interface from Manavins, right? We have another IPU product at Intel, which is FPGA-based big spring can here. I'm going to skip this as well. The only thing I mention is this product has a Vector block interface, quite a performing interface available. There's another presentation right after me from Intel talking about IPDK. In that presentation, Deb will explain details about this product, so I'm going to skip this. But I'm talking about it more from a solution point of view. If I want to offload this into IPU, right, what kind of ingredients I need and why IPU can help. So the first is block device interface to host, because now IPU has all this standard-based block interface, NVMe, Vector block, or any other interface, which can be fully leveraged, right, by this solution to expose another basically block device. Inside the block device, you can have root file system ready. So it's just the user interface we have today. The other thing is that everything here is dynamic, right? Because the container comes and goes, so you have to have some hotplug capability to expose a new block device interface to host, which has basically the root file system you need for running the function as a service containers. And then the next few steps are new, which can be done in IPU. One we mentioned earlier is the container image pooling and the caching. So IPU can just go to remote image registration servers to download images, and then unpack that into basically a root file system and expose that root file system into a BDEV, a block device, right? And as part of this unpack operation, there are some features from IPU can be fully leveraged on. For example, typically for a block device interface, it may support the clone snapshot feature, right? Which can be useful if you find that one root file system can be reused by many containers. And also decompression, as I mentioned earlier, IPU has an accelerator like Q80IP, which can be used to accelerate the decompression process. The other ingredients we need is to enable this offload flow, we need a communication path between IPU and the host container runtime software. So typically, it's just a RPC communication channel to enable this offload, so which I'll explain in the next few minutes. Right. Okay, so that's basically a very high-level view, and now let's spend a few minutes to talk about the detailed design, which explain how this can accelerate the function as a service. This is a concept level view. So today, on the host, right, you have a container runtime, like container D running, and then depends on different environments. If it's bare metal, typically you just need a run C to launch, start the containers. If you have like a secure container, for example, Kata container, which basically runs container in the VM, you can use the Kata agent to manage that containers, right, life cycle. So different environments. But in the IPU, as my previous presentation explained, has all the SPK, software stack, support BDEVs, and on top of that, it can expose BDEVs onto different device interface, like NVMe PF, VF, or Vector block device interface, right? The orchestrator is the remote system, right? Has the container images and everything here. Two new software components we add to enable this offload onto IPU. The first one is on the host. the container D has a very small software components, image management client, which enables communication to IPU, the image management service, right? So these are the two new software components we need to enable this whole offload solution. So it works like this. So first, if the orchestrator decide, okay, on this host, I need to launch a new container for this function as a service, right? So the image management client will get that request and is going to ask IPU. So it goes to this IPU image management service, which you need to do a few things, right? The first is to download the container image. So it can download the base image and any dynamic image, right, to local IPU here, cache into local storage or memory, right? So so that's perfectly fine for IPU to do, which can offload the overhead from host. But more importantly, right? So once you download the image here, you need to unpack the image and present that to host. So in this solution, it uses block device interface to present that image, right? So so this step 3 involves the basic unpack operation. So you basically need to decompose the image and get this root file system ready, and then just use a BDEV to expose that whole thing, right, to host. And then use hotplug capability to notify host, oh, now here I have a new BDEV available. In the NVMe case, it means a new namespace is available. If you use a value block, it means, okay, there's a new value block interface available to host, right? And also tell the image major client, okay, on that root file system image is ready. So now, if you run the bare metal container case, right, the runC can basically detect the namespace or the value block interface and load that, value block driver and mount the BDEV, right, into the right direction and make sure it's available to run the container. So basically that's the high-level flow. Right. So basically, it's basic concept level. These are the changes that we make, and 5 steps to get this whole thing up running. The next slide just describe the exact steps I was talking about, so I don't need to repeat it here, but it's just the details, like repeat what I said in previous slides. Okay. So the reverse sequence is also simple. The reverse sequence is basically if you want to destroy a container, that image client, right, service need to basically communicate to IPU image management service. So now the image management service can basically find out which BDEV is used for this root file system and or the container, so it can hot unplug the device block interface or detach the namespace, right? NVMe namespace case in the NVMe case, and it also can have some smart logic like reference counting, right? If no one is using this root file system anymore, it can destroy everything, like destroy the BDEV, free up that storage space. So next section is more details. This is just the POC. Ziye Yang and the team did prove the flow works. So he basically used runC to illustrate the commands he used. If you do everything here in host today, basically you typically do 3 steps. And in his example, he used runC. runC is the client to CLI tools to run the containers on Linux. This runC is based on open container interface, so it's more standard-based API to manage that container and run containers. And he used a very simple container image, the BZ box as example, right? So today on the host, typically takes 3 steps. The first step is to download the image. So you can use like a scopio command line and utility to basically run that operation, and then use UMOCI to unpack the image. Right, and then use runC to launch that root file system, right? Basically the container for container to use. So these are the 3 steps you do on the host. And if you do this in the IPU case, right, you basically just add 1 more step. But the first 3 steps are now can be done inside IPU, which is the same thing. You can use a scopity, right, to download the image and then unpack the image into BDEV. So when you do this unpack, if the same image is going to be shared by many containers, you can leverage on the snapshot, clone, and some other features to make that more efficient. And then step 3 is the one new, right, which need like hotplug BDEV into host and notify host, okay, some images are ready, available to use. And then the host will run the run C. So this is basically the 4 steps to do if you use IP to offload that image construction operations. Ziye Yang also has a plan to work on this new offload flow in the context of Kata container. Many of you probably know this Kata container, but basically it's different from the typical containers, application container, in a way that is more secure, right? So the containers are running inside the VM in the Kata agent case. So the left picture shows the current way the Kata agent is the one manage the container lifecycle and do all the image, construction preparation before a container can be launched. But the right picture here shows, okay, if you do the IP offload, you can move a lot of stuff into IP itself, which basically just need to enhance the Kata agent to include a image management client to communicate with IPU. And the IPU now can do all the work for host, right? You can download the image, unpack the image, expose that through BDEV, right? And then tell the host, okay, some block device is available. Then this Kata agent can get a notification from IP as well, and they can start, that whole thing, like launch the, mount the, the root file system, and then start the container. So it's basically the way to do in a Kata container case. Okay. I think that's pretty much what we have. So a quick summary. As I mentioned, this is more like an idea proposal. We did a POC, right? We think the IPU can help offload a lot of stuff for this kind of function as a service offload, like image pooling, root file system preparation. Once you move that into IPU, there are a lot of opportunity to optimize and to innovate, right? So the team did a POC, proved the flow works. So one example, right, for innovation. Today, we expose the BDEV, which is the standard block device interface to host. But that interface may not be the best interface for this kind of root file system. The ideal solution is just use another file system interface, right? Some of effort already ongoing. For example, there's this new volatile file system device interface. And IPU can implement this kind of volatile file system, right, which can expose the root file system, so it's more efficient. And you can also use the accelerator to do a lot of stuff. Compression, decompression, crypto, so which is going to help offload this kind of overhead from a host. But as I mentioned, it's more like a proposal. There's still a lot of work to do. So Ziye Yang and the team are working on the software development to build that control path, basically the image management client service to IPU image management service communication. So that's the control path we need to develop. And then we need to do a lot of performance evaluation and optimization as well. So that's pretty much what I have. So in the appendix, Ziye Yang added a lot of details, but I don't think I want to get into that. He's just trying to show the exact commands used to do this and show it works in the IPU. So it's more like a script level to show what to do in that FPGA IPU itself, right? So it's very detailed information just for anyone has interest to do this by themselves. Please just look at the appendix. But that's pretty much what I have. So if there's any question, please let me know. But I think it's very quick one. Any question? Any comments? Nope. Go ahead. You want? In this awful case, the IPs are running on host. The IP just used to prepare that image, right? Yeah, but the IP itself can run containers. So if you want to just say, oh, I have a software application running, maybe I can just package that everything in the container and run on the IPU. That's okay too. And so we can do that model. Okay. Andy?
How much percentage overhead do you think we can benefit from IPU? Specifically, when you're talking about snapshots, clone capability, you're using that capability to take it out from the native VDY. Put it on IPU, how much is that percentage?
We don't have that number yet. It's a very good question. That's one thing we want to do. So as a part of plan, we need to do that exact measurement, right? But today, depends on the function. I mean, the best container you can do today, right? If you get the whole container up running, the container itself can take almost like I mean, again, depends on the flavor container, right? But you're talking about like 100 milliseconds or even longer, that whole process. And if you want to download it, again, it takes longer. So one thing with IPU is the guy who owns the IPU, right, owns like infrastructure level. So he probably wouldn't know if I want to schedule a function as a service on this host, what kind of image I need to use, right? So he probably can just pre-download it, right? It means that this whole thing is maybe already ready in the IPU. So next time if I schedule the function as a service, the whole image should be just ready. So I just need to notify the host, okay, well, use this BDEV, use this whatever file system. So this whole overhead can be avoided, right? But again, I don't have data to show exactly, I mean, this whole thing takes 1 second or whatever, a few milliseconds. That's the one thing we want to figure out in next step. Okay. Okay. So I think Deb is just right here. So I think if there's no more question, I will just close today. But like I said, okay, this is a proposal, a new idea. There's work to do, but we think it's very interesting and it can open up some innovations. Especially we're looking into like a file system in kind of interface. Because for this proposal, the block device interface, from my point of view, is not the best option. You can just use another file system interface, which can expose the bundle, right, the root file system image for the container. So it's more efficient. And if you have a persistent memory in the IPU, it makes the whole flow even more efficient. So there are a lot of opportunity to explore. Okay, thank you.